Hi everyone, my name is Lauren Taus. I'm a psychedelic assisted therapist, an educator, and an activist for all the drugs. I'm here today with DoubleBlind to talk to you about the language of mushrooms. It turns out mushrooms have a language, and we're just figuring out how to decipher it. Mushrooms generate electrical signals that bear a striking resemblance to human nerve impulses. It's easy to see why most folks think of mushrooms as some type of weird plant popping out from under the soil when it rains and found in the vegetable aisle of the grocery store. Even scientists classified fungi as plants until as late as 1969. However, anyone with a bit of mycology knowledge will tell you that fungi are an entire kingdom of life unto themselves, having more in common genetically with animals than with plants. Magic mushrooms in particular are well known for their ability to affect our perception and mental states and have been used for thousands of years in various cultural and religious contexts. In contemporary psychedelic writing, people often talk about mushrooms communicating with them, such as in writer Bet Williams' account in her book, The Wild Kindness. She said, "The mushrooms speak to me, but I don't hear the words like you'd hear from another person talking. It's as if language arises in my own body, though it's nothing I'd come up with on my own. Sometimes I'm aware of fully formed sentences. Other times, whole systems of knowledge present themselves, devoid of any coherent words at all. Though some of us are eager to start a conversation with mushrooms, it's never been clear to scientists how mycelium communicates with itself. Sending information across the mycelial network is thought to be important in coordinating growth towards more favorable environments or deciding when to send out mushrooms. Sending information across the mycelial network is thought to be important in coordinating growth towards more favorable environments or deciding when to send out mushrooms. This rapid information transfer can be especially important in far-reaching mycelial colonies, which can cover thousands of acres of land in the case of the honey fungus, discovered in Oregon's Blue Mountains in 1998. Henry Munn was a writer, translator, and self-styled anthropologist. In a 1973 essay entitled The Mushrooms of Language, Munn wrote, "The Mazateks say that the mushrooms speak. If you ask a shaman where his imagery comes from, he's likely to reply, 'I didn't say it, the mushrooms did.' No mushroom speaks. That is a primitive anthropomorphization of the natural. Only man speaks. But he who eats these mushrooms, if he is a man of language, becomes endowed with an inspired capacity to speak." However, new research in the last few years may support the view of the Mazatec shamans and cast Munn's anthropomorphic assertions into question. Enter Andrew Adamatsky, professor of unconventional computing at the Department of Computer Science and Creative Technology at University of the West of England in Bristol, United Kingdom. Adamatsky and his team have studied the ways in which a whole range of microbes sense and react to their environment, and how such senses could be interpreted and applied by humans. Adamatsky's research has included the development of far-out ideas, such as wearable fungal biosensors that may one day act as a second skin, or evaluating the efficiency of a country's transport network using slime molds. In a subsection of Adamatsky's research, the team built on the discovery that many microbes, including fungi, generate electrical signals that bear a striking resemblance to human nerve impulses. Despite this resemblance, fungal electrical signals happen over minutes to hours, as opposed to the milliseconds our own neural signals are capable of. Working like an acupuncturist with a degree in computer science, Adamatsky and his team place needles connected to different electrodes into mycelium or mushrooms and record how these electrical signals change in response to various stimuli. Adamatsky and his team place needles connected to different electrodes into mycelium or mushrooms and record how these electrical signals change in response to various stimuli. In one experiment, the team showed how mycelium can be knocked out with chloroform, a commonly used anesthetic, only to regain its electrical activity after the anesthetic was removed. Other experiments have shown that the pattern of electrical activity changes in response to open flames, pressure, light, and food, as well as toxic chemicals such as ethanol. Electrical signaling in non-animal species such as plants, bacteria, and fungi has been known to scientists since at least the 1970s. The first two fungi found to respond to stimulation were the mycelium of oyster and honey mushrooms, and experiments conducted in 1995. Since then, very little research has been done on this discovery since it was picked up by Adamatsky in recent years. In 2022, Adamatsky and his team went on to document similar electrical signals in split-gill fungi, enokitaki, ghost fungi, cordyceps, and magic mushrooms like Psilocybe cubensis and Psilocybe tapensis. In one of the papers published in 2022, Adamatsky considered fungal electrical activity as a means of communication and found that although his language varies between different species, mycelial murmurings were shown to have a similar average word length to languages like English, Russian, and Greek. Fungal vocabulary was also found to contain up to 50 unique words. So how do we decode the language of fungi? Previous experiments with more obviously talkative non-human species, such as John Lilly's controversial NASA-funded experiments with LSD in dolphins, haven't always been particularly useful. Considering fungal language has only just been discovered, the path to deciphering it may be especially long. Just as they are slow thinkers, fungi might also be slow talkers, with Adamatsky suggesting in an interview with Merlin Sheldrake that a 10-minute human speech might take fungi 2 days to recite. Adamatsky states that deciphering these patterns of electrical activity could tell us a great deal about other ecological groups such as trees or insects, as fungi connect and interface with so much of the forest. In his paper on psilocybin-containing species, Adamatsky suggests that if humans could find a way to talk back to the fungi, we may be able to manipulate the mycelial network to enhance the production of mushrooms. In his work, Adamatsky also explores whether fungi having language means that they have consciousness. In a paper titled Fungal States of Minds, he and his colleagues explain that fungal organisms can perceive the outer world in a way similar to what animals sense. Then go on to ask, does that mean that they have full awareness of their environment and themselves? Is a fungus a conscious entity? Does that mean that they have full awareness of their environment and themselves? Is a fungus a conscious entity? Adamatsky states that deciphering these patterns of electrical activity could tell us a great deal about other ecological groups, such as trees or insects, as fungi connect and interface with so much of the forest. In his paper on psilocybin-containing species, Adamatsky suggests that if humans could find a way to talk back to the fungi, we may be able to manipulate the mycelial network to enhance the production of mushrooms. In his work, Adamatsky also explores whether fungi having language means they have consciousness. In a paper titled Fungal States of Minds, he and his colleagues explain that fungal organisms can perceive the outer world in a way similar to what animals sense. Then go on to ask, does that mean that they have full awareness of their environment and themselves? Is a fungus a conscious entity? Though there's a wider philosophical debate to be had on whether this fungal language implies a degree of fungal consciousness, Adamatsky is quick to explain that at the current moment it's not clear whether the linguistic complexity of fungi is the result of something close to intelligence or just a lot of random mycelial noise. Either way, translating this language may have some exciting future applications, such as biocomputing, a field in which the circuit boards are replaced with biological elements such as DNA or cells. The idea of biocomputers has been around since at least the 1990s, with recent advances including storing video content inside the cells of bacteria like E. coli. In one of the first papers on the subject of using fungi for biocomputing, Adamatsky suggests that the network of mycelium could be seen as a sort of naturally occurring ecological computer, which could be monitored by humans to tell us more about the health of the environment this mycelium occupies, or new areas of the forest it might be likely to grow into next. Taking this even further, Adamatsky suggested making buildings from living fungal blocks that can monitor the chemical status of both inside and outside the building, and interface with other electronics to open windows or switch on lights. In fact, a 2020 European Union funded project called Fungal Architecture seeks to do just that. Not only would such structures be able to sense the environment they're in, but also potentially be able to self-repair using sustainable materials. But what about the downsides? Do we risk being outsmarted by hyper-intelligent fungi in a day of the Triffids type scenario? Adamotsky suggests maybe not. Fungi have no need to rush. This means that fungal computers aren't likely to be grown in your office or rival the speed of our smartphones, but may still be valuable in places where speed is not critical, or more expensive sensors might be difficult to deploy. I don't know about you, but I'm real curious about the language of the mushrooms and keen to go slow in general. So I hope this conversation's been helpful for you, and I'm Lauren Taus with DoubleBlind. Let's listen to the mushrooms.